Okay, so today we're going to be studying immunology from first aid for step one. And I'm going to read along and discuss everything that we read and its significance to the first USMLE step one exam and your med school as well. So we're going to discuss some important things about med school as well. So starting off with the first page, I would like to shift your focus onto this great quote from Saul Goodman from Breaking Bad, which is that some people are immune to good advice. And this is 100% true. I approve it. This is a very good quote. And also, uh, this one from Batman and Robin, which you can read yourself. So always make sure to read these first pages of these sections. It has some interesting things, right? Starting off with lymphoid structure. So our immune system is basically the immune system has two kinds of organs, not two organs but two kinds of organs. So you have your primary organs and then you have your secondary organs. Now the primary organs are basically where the immune cells are made. So if you talk about origination of the immune cells, you're going to talk about primary organs. So you got only two primary organs. You have bone marrow, you have thymus. And the bone marrow from B, you can remember that it produces B cells. And from thymus, you can remember from the T, it produces T cells, right? T cells are matured in this. That there's a better way of saying this, that thymus does not make T cells. The production of T cells is the duty of bone marrow. So all immune cells are produced by the bone marrow. So bone marrow produces all the cells. From the bone marrow, there are some cells that can go towards the thymus, or there are some cells that can choose to remain in the bone marrow. So the cells that go to the thymus and get matured there, they are the T cells, and the cells that choose to remain there are the B cells. So it's more about which cells are matured where, that they get the differentiation. But T cells are also produced in the bone marrow and B cells are also produced in the bone marrow. So remember that bone marrow is responsible for the production, but then the maturation is what differs and what gives them their different properties. So that is the work of the primary organ. They are responsible for production and maturation of the cells. The secondary organs, which are all of these, are responsible for the collection of immune cells and their ability to carry out their function, the space where they carry out their function. So they are collected over there in these different organs, and then they carry out the function, they interact with the antigens, they produce their immunity, and then they do what they are made to do. So that's the basic function of the secondary organs. Secondary organs are basically offices where they are allowed to work at and where they carry out their function. So a lymph node, which is a secondary organ, has many afferents. So it means that has many entrances basically. So you can see that it has many entrances, but it has only one exit. So many entrances, but only one exit. So that's what they're saying, is that it's a secondary lymphoid organ that has many afferents, which is many entrances. So the blood can lymph, it's a lymphoid organ, so it receives lymph. So lymph can enter from many paths, but it can only go from one path. It has one or more efferents, so usually it has one, and it has encapsulated with trabeculae. So basically just these shells, basically these are known as trabeculae. So you can see this labeling over here as well, right? Their functions are non-specific filtration by macrophages and circulation of B and T cells and immune response activation. Basically, it's just a center for regulating your immune system. So this is where immune responses are basically originating from. So it contains macrophages, B and T cells. It also has plasma cells as well. So a fully packed, basically, immune system in a package. Now, the significance of having many afferents and only one efferent is that because there are many pathways from which the lymph is coming in, the filtration process gets easier, right? If it had only one entrance, there would be less efficient filtration because there is less amount of lymph coming in, right? But now a lot of lymph is coming in, right, from all over the body, and so at the same time, a lot of lymph is getting filtrated, and it's a lot of lymph is getting regularized, and then only the clean lymph, as we may say for simplicity's sake, is exited. So having many efforts is beneficial in that it has many. It is more an efficient process, and it's basically speeds up the process, right? So now that they're just describing the different parts of the lymph node, you're not expected to remember all of these parts. Just remember the clinical point of view on what the clinical significance is, and just keep in mind this picture, histological picture of lymph node can come. It's very easy. Basically, you can just identify many germinal centers over here. You can see these germinal centers. It's quite easy to identify lymph nodes. So a follicle is basically, it has B cells, right? It has B cells and it has germinal centers. So basically what I was marking over here, although these are germinal centers, but a better word for it would be a follicle. So these are follicles that I was marking over here, right? So all of these are follicles, as you can see. So follicles have B cells. This is what you need to remember. Primary follicles are dense and quiescent. Secondary follicles are pale. Germinal centers are active. So primary follicles and secondary follicles is just basically, you can say that the primary follicle is unactivated, right? So it is unactive. The secondary one is basically active. So that is the only difference, right? A primary can be a secondary one, and a secondary can also go back to being a primary one. That's the only difference. That when they get active, they are called as the secondary follicles, and they have B cells. The medulla is basically, now what we're going from out to inside, right? So medulla, right over here, you can see the medullary cords. They have plasmacytes and lymphocytes, right? And the paracortex has T cells. So basically, cortex is always the outer part. So always the outer part is always the cortex, and then after the cortex, you can see this is the paracortex. This is the cortex. So the paracortex has T cells. So they're describing paracortex separately because they want to tell you that it has T cells. So it contains high endothelial venules in which T cells enter the blood, underdeveloped in patients with DiGeorge syndrome. So this is a clinical point of view. So the paracortex is underdeveloped in patients with DiGeorge syndrome. To remember that. So follicles contain B cells, medulla contains plasma cells, and the paracortex contains the T cells. These are underdeveloped in patients with DiGeorge syndrome. Paracortex enlarges an extracellular immune response, which means EBV, or other viral infections, and it causes paracortical hyperplasia, which can give rise to lymphadenopathy. So just to clinical point of view, again, you need to remember this, that in EBV or infectious mononucleosis or other viral infections, lymphadenopathy occurs due to paracortical hyperplasia. So you need to keep this in mind. So this is how you basically study histology or anatomy. So you just remember the clinical point of view, and that's it. That's when you're solving questions, you get to solidify all this information once and for all. So that's basically it uh, for this page. This is just the location of all the lymphatic drainage and lymph nodes present throughout your body. So it's good to remember all of this, but I will tell you the important ones. So in the lymph nodes, basically we'll go through all of them, but I'll tell you the important ones. So if you have submandibular or submental lymph nodes which are enlarged, right? So basically they are present over here. So now you must, like, it's very easy to remember that they will be draining obviously the face, the oral cavity, the anterior term. So any malignancy of the oral cavity is going to enlarge them. Okay, deep cervical is a bit difficult to remember because it can be diffusely enlarged in a lot of pathologies, but because deep cervical is in your neck and oropharynx, so you can remember that the malignancy of the head and neck and oropharynx can cause this. But again, Kawasaki, infectious mononucleosis, and URTIs can also cause this. That's important for that to remember. But you can remember this one, the first one. Supraclavicular is important to remember because the left one is known as the Virchow node, and that's just a name for the left supraclavicular one, and that's just the important point, right, for it, the second name for it. Mediastinal one can also is important to remember, and then the important point is that pulmonary TB can cause a unilateral hilar lymphadenopathy, and sarcoidosis can cause a bilateral hilar lymphadenopathy. So you have to remember both of them. Very, very important. Very high yield. The difference between them. And obviously, because they're in the lungs, so they can be enlarged by lung cancer as well. All right. Axillary is important. Of course, breast cancer is very important point. So it can be a sign of breast cancer. It can be enlarged in mastitis. So mastitis is also inflammation of the breast. And epitrochlear is not that important. It can be enlarged in secondary syphilis. It is written here, but I've never seen this point being tested. Celiac, supramesenteric, inferior mesenteric, they all can be disturbed in abdominal inflammatory diseases such as the celiac disease, inflammatory bowel disease. The important one is Sister Mary Joseph node, which is a periumbilical one. This is important because this is sorely enlarged in gastric cancer. So remember this. It's known as Sister Mary Joseph nodule, right? And para-aortic ones can be enlarged in metastasis of the testes or the ovaries. So kidneys and fallopian tube and everything, it can be guessed, but the para-aortic ones drain the testes and the ovaries. So you need to remember this. It's an important point because they are up over here and the testes and ovaries are down over here. So like the testes are down here, the ovaries are over here. So people often forget, but you need to keep this in mind. Iliac, it's pretty efficient. It's okay. So yeah, so these are important, right? Submandibular, submental, supraclavicular, mediastinal, axillary, Sister Mary Joseph nodule, para-aortic. So keep these in mind. We can remember, read and remember others as well, but these are more important. Spleen, secondary lymphoid organ. It is located in the left upper quadrant of abdomen, anterior to the left kidney, protected by the 9th to 11th ribs. So normally you cannot palpate the spleen in abdominal examination. Splenic dysfunction can occur in post-splenectomy cases, in sickle cell disease, in which it is known as autosplenectomy, and this can cause decreased IgM and decrease complement activation, which gives rise to decrease C3b activation, C3b opsonization, which gives rise to increased susceptibility to encapsulated organisms. So what is this whole concept? Concept basically is that to remove the encapsulated organisms, you need C3b, right? So C3b needs to be opsonized, right? Opsonization just means activation in simple terms. So to remove encapsulated organisms, you need C3b. And opsonization is a function of complement system, right? We're going to study it in this section in itself. However, and for complement system to work, you need IgM. So it's I think the classic pathway, if I remember correctly, which gives rise to C3b opsonization, and the classic pathway is regulated by two Ig proteins, which are IgM and IgG. So we're going to study this in detail in this section, but as you can see, because the spleen is removed, now you have less IgM, which gives rise to the lack of proper functioning of the complement system and the lack of C3b opsonization, which gives rise to increased susceptibility to encapsulated organisms. This is a whole chain of events that is problematic for the patient. So for encapsulated organisms, I want you to remember that you need C3b opsonization, you need IgM, and basically for all of this, you need a spleen, a good working spleen. What will you find in the blood of a patient who has post-splenectomy? So either the patient has undergone splenectomy, either he has undergone autosplenectomy, if he is a sickle cell patient. What findings will you find? So you will find Howell-Jolly bodies, which are nuclear remnants in the RBCs. You will find target cells, you will find thrombocytosis. Spleen basically has a lot of platelets stored inside of it. So if you remove the spleen, a lot of those platelets are going to be released to the blood, which is not good because then you don't have a reserve store for the platelets. You don't have any reserved store for them. And you also get lymphocytosis. So what does spleen do is spleen stores the thrombocytes and the lymphocytes inside itself. So when you basically need them, it releases them. But if you don't have spleen, then that process will not occur. And that is a bad thing because then you don't have a reserve store of these important cells. Now whatever you lose, you lose it entirely. So you cannot rely on any backup for such kind of a situation. And so very important, you should vaccinate patients undergoing splenectomy or with splenic dysfunction, both against encapsulated organisms, which are three ones which you absolutely do need to remember forever. And they are pneumococci, HIB, and meningococci. So you need to remember this forever. I will put 2 stars signifying the importance of it. Maybe I'll put 3 because this is very important. So as long as you are a doctor, you need to remember all 3 of them. And this goes back to this point of encapsulated organisms. So I hope this was clear. Periarterial lymphatic sheath. Now these are just the structures of the spleen. So not important, but it's good to know that periarterial lymphatic sheath contains the white pulp and it has the T cells. Follicles, they contain the B cells. It is located within the white pulp. And it also has a marginal zone, which basically gets activated when there is an infection. So this is a site where you have antigen presenting cells which capture antigens for recognition by lymphocytes. So this is located between red pulp and white pulp. So let's to go through it. Again, there is a white pulp, there is a red pulp. The red pulp contains the sinusoids, the reticular fibrous network, basically everything related to blood. So blood, red pulp, everything related to blood. The white pulp contains everything related to the immune system. So the white pulp contains the T cells, the white pulp contains the B cells, the white pulp contains the antigen presenting cells, and that's pretty much it. What is a sinusoid? Sinusoids are big vessels you can see. Which these are labeled as, or here, these are dilated vessels, and dilated vessels allow more blood to come in so that at the same time, more blood can be filtered. Reticular fibrous framework is basically a filtration mesh, kind of a filtration system which filters these sinusoids. So if I were to show you an example, if this is a dilated vessel and you have this meshwork, kind of a fibrous, you can say a filtration meshwork, it basically filters the microorganisms, the antigens and everything, and the dead RBCs. So these are small spaces. A healthy RBC, a healthy cell can pass through them because it's a flexible cell. An old cell will not pass through them because the flexibility of the cell decreases with its age. So what happens is that the old RBCs get trapped. So that if I could show you a better illustration. So this, let's say, is a vessel, right? Dilated vessel. This is the reticular fibrous meshwork. Okay. Now a healthy RBC is going to pass through it because it is flexible. An old RBC will not pass through, right? So it will not pass through it. This can pass through it because it is not flexible. All right. So this is the function of the reticular meshwork. So this is the function of the reticular fibrous framework, and these are your sinusoids. Just looking at the spelling. So this is what comprises of the red pulp. That's basically it. That's it. Okay. So I hope the screen was clear. These are the important points that you need to remember. Going to the thymus. So located in the anterior, superior, and mediastinum, site of T cell differentiation and maturation. You already covered that. Encapsulated. Thymus epithelium is derived from third pharyngeal pouch. So for step 1 purposes, you need to remember this small detail. For med school purposes, it's very important. Med school seems to love this kind of detail. Whereas the thymic lymphocytes are of the mesodermal origin. So the lymphocytes of the mesodermal origin, the epithelium is of the endodermal origin. Cortex is dense with immature T cells. Medulla is pale with mature T cells. So medulla has mature, M for M. right? Cortex naturally has immature, and hence Hassel corpuses containing epithelial reticular cells. So Hassel corpuses are basically just small cells, not important detail at all. The X-ray is important. We just look at it in just a minute. So what it says is that the thymus is basically visible in normal units, and it involutes by the age of 3. So by 3 years, you cannot see thymus in the X-ray. So absent thymic shadow or hypoplastic thymus seen in neonates, right? Neonates. So neonates, you can normally see thymus. If you cannot see it in the neonates, then there is some problem. So absent thymic shadow or any problem in which you're not able to see the thymus, it means that there is some immunodeficiency, a severe combined immunodeficiency, or DiGeorge syndrome, whichever, and it could be any of them. But this is the problem. A thymoma is when there is a neoplasm in the thymus. Now you can see thymus in you can see a bigger thymus in the neonates, or you can even see thymus in older individuals. That is what thymoma means. So either a bigger thymus in the neonates or a persistent thymus in the adults. Very important, associated with myasthenia gravis. Very important. Superior vena cava syndrome, pure cell red aplasia, and good syndrome. So we'll study them in future episodes, but myasthenia gravis, you must remember, very, very important. Myasthenia gravis and superior vena cava syndrome, both are very important. So thymus X-ray, right? So thymus on X-ray, just look at it. It's a triangular sail sign. Why do they call it that? It's a good X-ray. You can see. You can see this thymus stripe over here. Can we see it here? No. There is no thymus. Where is it? Where is it? Where? So you can see this again. This also thymus, which is the sail sign, right? This is a very good picture. This right over here, sail sign. Remember, it is known as a triangular sail sign. So that was it for the histology of immunology. So histology of immunology. Okay, so cellular components of immunology now. So now we first looked at you can say the histology of immunology, and now we're looking at basically starting to dive into the physiology of our immune system. So starting off with what kind of cells are involved. So we already know the organs, but now we're just going to look at the cells that are involved, right? So starting off, we have the innate immunity and the adaptive immunity. The innate immunity is a sort of, you can say, first line immunity, and the adaptive immunity is sort of, you can say that the last line of immunity. That's the most advanced immunity. So if you can remember this, that by A, you can remember that this is an advanced kind of an immunity, and an innate is sort of an initial, you could say, like initial, right? So if I were to write it over here, so this could be an initial kind of an immunity, right? You have to forgive my writing, and this could be advanced. So you could say, I could write advanced. All right. So this is how I try to remember the differences between them, and everything that is written in these two columns follows the same theme. So innate immunity is going to follow every little bit of step of an initial kind of immunity. So every single point that you go through is going to show that this is an initial kind of an immunity. And every single point that you go through in this column is going to show you that this is an advanced kind of immunity. So starting off with the components, neutrophils, macrophages, monocytes, dendritic cells, natural killer cells, and complement system, physical epithelial barriers, enzymes. So everything that is that you would expect to work at an initial response. One thing that is important is that natural killer cells are of lymphoid origin, right? So lymphocytes are a part of an adaptive immunity, but only one kind of a lymphocyte that is part of the innate immunity is a natural killer cell. So you have to remember this is an important point, that natural killer cells are basically lymphocytes which are a part of the innate immunity. The adaptive immunity it has T cells, B cells, and circulating antibodies. So lymphocytes are present in the adaptive immunity. Mechanism is basically through what mechanism they bring about their immunity. So for these cells, they have a germline encoded kind of a mechanism in which they have a certain specific mechanism. That mechanism is not going to change, it's not going to adapt, it's not going to be variable. They have a simple function. Every cell has a simple function. These are cells, they have a simple function, and they will carry that out and they will die, and then new cells will be formed. That's what germline encoded means, that they have a decided specific function through their germline, through their DNA. The adaptive immunity, however, is adaptive, so it keeps on changing, right? It has variation in it. So the reason why they have this variation in it, because these are also cells, but they have this variation is because they have this process known as the VDJ recombination that happens during the lymphocyte development. So what this process is, we're going to look at it after a certain while, but through this process that they can adapt, and they can incorporate new mechanisms to intervene in an infection. So new antigens or new viruses that you come across in your life, they can adapt with it, and they can fight them off if you come across them again in the future. So this is why this is the adaptive immunity, because it adapts to the infection. Response to pathogens is obviously non-specific. In the innate immunity, it occurs rapidly, minutes to hours, because if you have an initial response, you want it to occur quickly, and it has no memory response. Adaptive immunity is highly specific, it's refined over time, and it develops over long periods. Memory response is faster and more robust. Secreted proteins, so I prefer to remember the ones that are involved in the adaptive immunity system: immunoglobulins, which are your antibodies, and cytokines. So remember these two, and the other ones you can sort of keep in mind that they are from the innate immunity system. And the key features in pathogen recognition. Now this part here is something that you will learn throughout the course of our reading here, but just a small review of what this is. So the way that innate immunity recognizes pathogens is through toll-like receptors, pattern recognition receptors, molecular pattern at the antigens, and that lead to activation of NF-kappa B, and NF-kappa B then leads to the activation of your innate immunity system. So examples of pattern associated pathogens in which they help to identify is lipopolysaccharide, which is in the gram-negative bacteria, the flagellin, which is in bacteria, generally present in the bacteria, the nucleic acid, which is present in the viruses. So these things, they are basically few examples of pathogen associated molecular patterns. So these patterns are recognized by these toll-like receptors, and which activate NF-kappa B and leads to their innate system getting activated. So more on this later. This system has memory, so it would obviously have memory cells. So activated B and T cells, which are subsequent to exposure to a previously encountered antigen, they get activated stronger and result in a more quicker immune response. adaptive immunity decreases with age. That's the only downside of it. So you need to know that senescence means age, right? So immunosenescence means that the immune response decreases with age. Okay. Immune privilege, organs, eye, brain, placenta, testes, and tissues where chemical or physical mechanisms limit immune responses to foreign antigens to avoid damage that would occur from inflammatory sequelae. Allograft rejection at these sites is less likely. So what that basically means is that your brain, placenta, testes and your eyes as well, they have certain proteins that have the chance to get recognized as foreign proteins in your body. So what happens is that these organs, so let me show you an illustration. Right? So what happens is, let's just say that this is an organ and it has some it has some protein which has the potential to get recognized as a foreign protein. It will have a strong membrane surrounding it so that this protein is not exposed to the general environment of the body, because if it is exposed, then your immune cells are going to come and they are going to destroy it, right? Let's say, for example, your sperm, right? So sperm is a foreign protein, right? It's supposed to go into another person's body and carry out fertilization there. So it has a chance to get recognized as a foreign protein. So what happens is that they have strong membranes surrounding it, which lead to the immune system not interfering and not recognizing them as a foreign protein and not destroying them in the process. Right. So you must have heard of that infection. I'm going to describe it in detail afterwards. Is that when one eye's barrier gets destroyed in an injury or something, the patient starts losing his eyesight in the another eye, which is not damaged. That happens is because the proteins present inside the eyes, they're exposed to the blood, and the immune system starts to recognize them, and so it starts attacking the proteins of the other eye as well. So this is what happens. Okay, this is a small phenomenon known as immune privilege. Is that these tissues, although they have the potential to be recognized as foreign, they are still they are still protected from the immune system to avoid damage. And if you do allograft transplantation at these places, then they would have a less chance of rejection because the immune system is not that strong at these places. So they would have a less chance of getting detected and getting rejected. All right. So MHC, which is a major histocompatibility complex 1 and 2. MHC is encoded by HLA genes. These are the same genes that are present in your which you look at in your transplantation and transplantation matching and all of that. So they present antigen fragments to T cells and bind T cell receptors. That is their function. That is their important function, is that they present antigen fragments to T cells and bind the receptors. Now there are two types, MHC1 and MHC2. So MHC1, a simple way to remember is that they have HLA A, B, C, and MHC2 all of them have D, but they just have PQR with them. So it's very easy to remember. The mnemonic that is written here is that MHC1 have one letter, which is ABC, and MHC2 have two letters, which is DP, DQ, DR. So it's very easy to remember that. MHC1, they bind to CD8, and MHC2, they bind to CD4. So the easy way to remember them is that you need to get the number 8, right? So what will you multiply by CD8 to get 8? You will multiply 1. So CD8 multiplied by MHC1 will give you 8. So this is how you must remember that MHC1 binds to CD8. But for in order to get 8 with CD4 you have to multiply it by 2. So CD4 gets bound to MHC2. This is a small, you wanted to remember that. Structure, you don't really need to remember. Expression, all nucleated cells, antigen presenting cells and platelets except RBCs have MHC1. So very important point, remember that. Antigen presenting cells of MHC2. Okay, so all nucleated cells have MHC1, only antigen presenting cells have MHC2, right? Antigen presenting cells naturally would have MHC1 and 2 because they also have a nucleus, right? So this is a very important point to remember. They present endogenous antigens, viral or cytosolic proteins to CD8 cytotoxic cells, and they present exogenous antigens to CD4 helper cells. So because they are present on all cells, they would present problems in the cells that are already present in the body, right? Let's say, for example, if a cell does not have MHC1, but it should have, it's a nucleated cell, it is present in our body, it should have MHC1, but it doesn't. What is the meaning of it? It means that there is some endogenous problem going on, something going on from inside the cell. Whereas if an antigen presenting cell has an MHC2, it shouldn't have, naturally it shouldn't, but it has an MHC2, which means that the exogenous infection or a bacterial infection has occurred. So MHC2 are, for CD4 cells, they bind to APCs and they usually present bacteria. Whereas MHC1, they present viral or cytosolic proteins. They also present, you can say, tumor, because tumor is also an inside thing of the body, an endogenous thing. So tumor is also presented by MHC1. But you have to remember these differences. Antigen peptides loaded onto MHC1 in rough endoplasmic reticulum after delivery via transport associated with antigen processing. And this is loaded by the release of an invariant chain and an acidified endosome. So remember the difference. This is MHC1 is related to transporter associated with antigen processing, and MHC2 is related to invariant chain. The detail of this is just basically not important. And beta 2 macroglobulin is associated with MHC1, invariant chain is associated with MHC2. These are just small memory things, not really that high yield, but just if you can remember, it's very good. And this is the structure of both MHC1 and MHC2, and this is where basically there's a difference. So this has a beta 2 microglobulin chain, and this has a beta 2 chain. So this is a short microglobulin chain, this is a long beta 2 chain. Yeah, so you can see that this has two equal length chains, 2 alpha and 2 beta, and this has one long and one short chain. So just go through this. This is a difference. So MHC1 has a short chain and a tall chain, and MHC2 has both long chains, right? Now these are some HLA subtypes that are associated with disease, and this is just plain memorization. But if you're going through studying through step 1, you will encounter these throughout your preparation. So this is very important. Like, this is very high yield to remember. But you are going to remember them eventually. Like, looking at this table, you might think that you have to do rote memorization of it, but that's not the case, because you will encounter them multiple times throughout your preparation. So it's not a big deal. Psoriatic arthritis, ankylosing spondylitis, IBD, reactive arthritis. Mnemonic is PAIR for B27. Abacavir hypersensitivity, which is abacavir is a antiretroviral medicine. It's associated with HLA, with B57. DQ2 and DQ8 is associated with celiac disease, and DR3 associated with diabetes mellitus, SLE, Graves' disease, Hashimoto, basically all your autoimmune diseases, and DR4 is associated with rheumatoid arthritis mainly. So I would want you to remember rheumatoid arthritis mainly, SLE and Graves' disease for this. And celiac is obviously DQ2 and DQ8. So you must remember this table, it's very important. but I wouldn't stress it because you will remember it eventually throughout your preparation. So the functions of natural killer cells is that this is a lymphocyte member of the innate immune system, like I told you, and they use perforin and granzymes to induce apoptosis of virally infected cells and tumor cells. So perforin and granzymes are basically just what they do is they're just proteins present on the natural killer cells. So these are the natural killer cells, right? And they have these proteins present as perforin, and then inside them, this is basically perforin. If I could label them as P, and inside them they have these granzymes. So what they do is they puncture a hole in another cell, and then these granzymes enter the cell, and then they digest the intracellular material of the other cells. So this is how they induce apoptosis. So apoptosis, you must remember that it is induced by three different types of pathways. So one of them is granzyme pathway. They are actively enhanced by IL-2, IL-12, interferon alpha, interferon beta. So remember this. This is important. And they are induced to kill when exposed to a non-specific activation signal on target cell or to an absence of an inhibitory signal such as MHC1 on target cell. Again, if MHC1 is not present, then of course it's I would say a very non-specific activation signal, and that is going to give rise to NK cells to get activated. Right. They also kill via an antibody-dependent cell-mediated cytotoxicity, in which CD16 binds Fc region of the bound IgG. So if I could show you, just a mechanism of how natural killer cells they carry out their immunity. So natural killer cells can directly kill a cell, in which they sort of use a perforin and granzymes mechanism, and what they could do is they could get bound to an antibody that is already present to an antigen, bound to it. So it says antibody dependent cellular toxicity. So they could get bound to it, and then they could just carry out their cytotoxicity. They could just carry out their granzyme part. So these are just two ways to kill an antigen, basically. Is that either they could directly kill it, or they could use an antibody that is already bound. Let's say if this is an antigen, right, and this is an NK cell. So there's two ways to kill it. Either it can use the perforin granzyme pathway, or it could get attached to an antibody that is already present to it. It could get attached to it and then carry out its pathway, right? So this would have a lot of antibodies attached to it. Obviously, this is an antigen. So this is how these are just two ways and they can kill it. So you don't really need to know the detail of it, but you just have to know what this means. So that's pretty much it. So major functions of B cells and T cells. B cells is very easy. Your humoral immunity, the clients in present antigen undergo somatic hypermutation. For antigen specificity, this is just a process in which they just get variation in their function. They produce antibodies, which differentiate into plasma cells to secrete specific immunoglobulins, and they maintain immunologic memory. So memory B cells, they can persist and accelerate future response to antigen. T cells are cell-mediated immunity. CD4 T cells are B cells, make antibodies and produce cytokines to recruit phagocytes and activate other leukocytes. CD8 T cells directly kill virus infected and tumor cells via perforating enzymes. So it's already told you guys, so that you just remember that they kill viruses through this. And CD4 they help make B cells make antibodies and produce cytokines to recruit phagocytes and activate other leukocytes. So this difference you have to keep in mind. And they are involved in the type 4 hypersensitivity reaction and acute and chronic cellular rejection. One thing that you must keep in mind, B cells, they differentiate into plasma cells to secrete specific immunoglobulins. These are the antibodies, right? Plasma cells are basically what they secrete immunoglobulins. They are mature B cells, kind of mature B cells, you can say. And right here, we have the differentiation of T cells. So how the T cells get differentiated? It's very easy. So they are formed from the bone marrow, okay, and then they go to the thymus, because the thymus has a T, and a T means that the T cells get mature there. So what happens is that the cell has, when the T cells get into the thymus, they have both the CD4 positive and CD8 positive antigens. And what happens is when they move from the cortex to the medulla, so when the cells initially the cells reach the cortex of the thymus, they have both the antigens. When they move towards the medulla, then they start getting specific. So when they're moving towards the medulla, what happens is they negative selection happens, in which they lose one of their antigen. So what this positive selection mean is that those cells with both the antigens are selected and they move forward. If there's a defect in this part, when we use that, if there are cells in the cortex that only have one antigen, they will not get selected. They will not move forward, because in order to move forward, in order to get promoted, you need to have both the antigens when you're at the cortex. So this is a positive selection. Negative selection, you will be selected when you have either a CD8 or CD4 positive, when you have one antigen. All those cells that have two antigens at this point will not get selected. Only those cells which have a one antigen, which have matured, will get selected and they will move forward. So this is just a small kind of a selection process. Those cells which have CD8 positive receptors, they will form cytotoxic cells. Those cells which have CD4 positive cells would form helper cells. And what happens is that these helper cells then go to the lymph node, and then obviously through the connection of different interleukins and different proteins, they get formed into either Th1, Th2, Th17 or T regulatory cell. So what proteins are they? So the helper cells are basically present when these cytokines, such as interferon gamma, let's take one helper cell. Let's take one helper cell. So we have one helper cell. So I would say this is a helper cell, right? So we have one helper cell, right? We have one helper cell, right? Now, if on this helper cell we interferon gamma and interleukin 12 work, they act on this cell, what's going to happen is it's going to get transformed into a Th1 cell, right? It's going to transform into a Th1 cell, and after it transforms into Th1 cell, it's going to secrete interferon gamma and interleukin 2. Interleukin 2 is important, which in itself it activates the macrophages and cytotoxic T cells. So this is how an immunity is going to be carried out. Let's say this helper cell is resting in the lymph node. An antigen comes, and that antigen forces the immune system to release these cytokines. These cytokines will in turn act on the resting helper cell, transform it into a Th1 cell, and then that Th1 cell is going to secrete interferon gamma or interleukin 2 to activate the macrophages or cytotoxic T cells. Right. Now, what kind of protein works, gets released, depends on the type of antigen. So keep that in mind. The same concept follows for the always. So if on a helper T cell, interleukin 2 and interleukin 4 get activated, attached, it's going to form Th2 cells, which is going to secrete these proteins. These are going to activate 4, 5, 6, 10, 30. These are going to activate eosinophils or IgEs, right? Now you have to remember all this. You have to keep in mind the minus sign shows that when these will act, this is going to suppress the formation of Th1 cells, and these proteins is going to promote the formation of Th1 cells. Similarly, if TGF beta, interleukin 1 and 6 get act on the helper T cell, they form TS17, and the TS17 cells, they form IL-17, IL-21 and 22. They induce neutrophilic infiltration, and if EGF beta and interleukin 2 act on the helper T cells, they activate the T regulatory cells, and then they secrete these proteins which prevent autoimmunity. So T regulatory cells, they prevent autoimmunity. So that what they do is they shut down the immune system to prevent too much damage. That's what they do, right? So this is basically what this whole table shows you. Now this might look a bit overwhelming, but trust me, it's easier to remember them once you go along. It's very easy. So it's quite easy to remember them, and we're going to go through it one more time so that you understand.